Good morning. I'm delighted to start off the SoSAFE workshop with a talk about the Dry Lake Valley site along the central San Andreas Fault, where we've learned quite a bit about structures formed from both modern and prehistoric creep and how they're expressed in trench investigations. The background image here is looking to the southeast of the Dry Lake Valley site, and I want to draw your attention to the quite spectacular and steep tectonic geomorphology in this creeping environment. There have been numerous co-authors and collaborators that have helped me a lot with this research. I'd also like to acknowledge them right up front. So, the motivation for studying the central creeping section of the San Andreas Fault is to understand its slip behavior over long time spans, over geologic time, to address the question of whether or not there are earthquake ruptures that break through this part of the fault, perhaps participating in southern or northern San Andreas Fault events, or having its own large earthquakes. So essentially what we're trying to do is test the validity of models coming from sources such as SoSAFE, which present outcomes showing that large earthquakes, larger than we've seen in the geologic and historical record thus far, do break through these creeping parts of faults over timescales that are relevant to humans. And so we want to do a test of that, and that's what this study is all about. Okay, so what we're going to go through in this talk is, of course, the location of the site and kind of some context there. We'll look at the paleoseismic excavations and observations from the site, as well as kind of a fortuitous opportunity to study rupture patterns on the surface from surface creep. And we measured these using structure from motion, and they developed because of this extreme California drought of 2013-14. And then we'll get into the overall findings of the study. Okay, so this site, the Dry Lake Valley site, is located in that central creeping section of the fault, shown in the map on the left with the red and orange warm colors correlating to creep rates from Tong et al. 2013. At this particular location, creep rate from that study is on the order of greater than 20 millimeters per year. And I just also want to draw your attention to the other stars on the right graphic, which show the latitudes at which other geologic investigations of the creeping section have been studied. And I'll just say that those locations have also not thus far found any evidence for earthquakes of large magnitude. So other contexts, so in 1857 to the southeast of the creeping section, possibly extending into the creeping section, there was the Great 1857 earthquake. And in 1906, there's the San Francisco earthquake as well. And so the question is, do these large earthquakes sometimes break into Dry Lake Valley site and the creeping section, or could there be other events in between which rupture the ground surface? So looking for earthquakes in a creeping environment is challenging because evidence of faulting does not necessarily mean evidence of earthquakes here. Evidence of earthquakes, in this case, has to be evidence of large ground displacements, either free face fault surfaces that are eroded back and forming colluvial wedges, or open ground fissures which are filled in with sidewall material, evidencing their large opening due to large ground deformation from large earthquakes. So we studied the Dry Lake Valley site, which is in a relatively straight section of the creeping segment of the fault. Our site was just at the very southeast end of what's known as the Dry Lake Valley. And here we opened 9 trenches, and the trenches sampled through stratigraphy of different origins, including sag fill, which is filled by both ephemeral fluvial deposits and colluvium, and then alluvial fan material, both of old origin, which the sag pond is developed within, and then younger alluvial fan material that's active today. I also want to key you into these yellow lines here, which represent the location of the 2014 ground rupture that we saw at the site and documented that rupture due to creep. But before we get to that, we want to look at these 3 trenches as a sample of what we saw overall at the site. Trench 1, moving to the northwest, Trench 4, along the Sag Pond Scarp colluvial environment, and to Trench 7 on a late Holocene alluvial fan. So zooming into Trench 1, which extended across the Sag Pond, we notice on each side of the Sag Pond 2 wide shear zones. So on the left side, we're looking at a hand log of the southwest shear zone. On the right side, we're looking at a photomosaic of the northeast shear zone. And in both of these representations, what we saw in the trench, we see pervasive cracking or fractures throughout these shear zones. The shear zones are relatively wide, greater than 7 meters. There's overall what we would classify as significant deformation and displacements across the zone, and that's owing to the fact that there's quite a bit of time on this rapid fault. And then finally, the pervasive ground cracks, the fractures, are almost all that we have observed are 45 degrees about clockwise oblique to the overall fault trend through the site. Last thing I'll say is that in 2012 we were doing hand logging in concert with photo documentation, which is a stark contrast to what we're doing in 2013, where we started using AgiSoft PhotoScan to do structure for motion documentation of the site and subsequently photo logging on top of really nicely orthorectified imagery from those models. And this is an example of that, T4. So in T4, we were sampling across uplifted 7-meter high fault scarp. And so what we see here overall is, on the left side, lighter stratigraphy. This is old alluvial fan material. On the right side, we see dark colluvial wedge material. Colluvial mass material. There's no individual colluvial wedges that we see in here. It's just kind of monotonous gray material, which we infer, therefore, to develop through progressive, with time, kind of steady creep along the fault, uplift and erosion of the soil A horizons deposited on the Sag Pond side. Here's an example of one of the nice things about using structure from motion to document these trench investigations. We can take many photos from slightly different angles and start to, even though we're logging in 2 dimensions in orthophotos, start to get a sense for the 3-dimensionality of structures in the trench. So we can kind of rotate into the trend of fractures like we're doing here, zoom in, kind of see the deformation. It's really important in these really subtle features. Okay, last trench that we'll look at was T7, which is in younger alluvial fan material. Here the stratigraphy is from about 2,500 years and younger. And across this 13-meter long trench, we see, again, this pervasive cracking. We see it both in the red lines on the logging above, and also you can just see the cracks in the stratigraphy on the photomosaic below. And you might notice that some of the cracks don't go all the way through top to bottom in the trench. That is partially due to different, probably different time spans of activity of these fractures, but also because of their geometry and their opening mode. They may extend to certain depths, and then as their orientation relative to the cut of the trench, we may only see part of them exposed as well. One thing that we did see in this trench were 2 larger opened fractures that were filled with material at some point in the past, what appears to be prior to about 100 BC. And so one might infer that, okay, well, maybe this is evidence of a larger magnitude rupture through this zone because we have this kind of open crack 4 or 5 centimeters filled with material. Obviously, it's not great evidence for a really large earthquake through the site, but perhaps more than we've seen over the historical period. But we're about to see that there's other models, natural models without large earthquakes, that can get this sort of deformation. And so that is that the ground ruptures from creep in times of extreme drought along the creeping section of this fault and others as well. And so the thing that we noted that was important is these sites that we're studying, and just generally this part of the fault, is pretty nice clay-rich soils that in times of drought and seasonal times we notice ground cracking, polygonal, in different areas. And so they're very stiff soils. And we notice that, okay, from Utah, we're looking and seeing a really impressive drought occurring in California and thinking, well, okay, with time, these stiff soils are not shrinking and swelling and healing from rain over quite a long time period. In fact, we looked at rain gauges nearby and noticed no events which could have produced soil shrink swelling from at least December 2012 to September 2014. And so we wondered, would these soils produce ground cracking as that we see in statically stiff roads? And so we went to the site, and indeed we saw this at multiple locations along the creeping segment. So here is the DeRose Winery offset canal, and then in the foreground we see these cracks that are oriented into crack sets going along the San Andreas Fault trend here. And then here's an example of what they look like at our site, and we'll zoom into that now. So here is here are the fractures that we documented at the Dry Lake Valley site, and we did this using structure from motion, using 3 different data sets that we collected. One producing a 9 centimeter grid model, one producing a 2 centimeter grid model, and one producing a millimeter scale model, and we're showing the orthophoto here. And so from the lower resolutions, we can see nicely the overall array of left-stepping crack sets. We interpret these are incipient R shears. And but to really document the opening of these cracks, we needed to zoom into the 1 millimeter model. And so we only made that model by hand over a certain subsample of the site. And so in total, we sampled 28 R shears at that zone, where there were 119 opening mode fractures that we documented. These we infer, again, that have occurred over about 1.8 years of time. Okay, so the mean fracture opening that we documented was about 1.8 centimeters, and assuming a model of simple shear with pretty minimal rotation across about a 1 meter wide zone that these fractures go through the shear zone is, we then use this model to infer about 4.8 centimeters of right lateral slip. With all the uncertainty, it could be between 3.7 and 6.5 centimeters. And that's important because we see that over this really narrow zone of only about a meter, we're basically seeing all of the creep that one would expect based upon prior geodetic studies, which would estimate anywhere between 3 and 5.5 centimeters of right lateral slip from creep over this time frame. And so overall, the site, the ground rupture at the site matches really well from what we're seeing in the trenches. And because we see no other evidence for different types of deformation within these trenches, and because we know that the very little deformation, kind of minor openings that we see can be produced along the creeping fault in times of drought, we don't see really any good evidence for ground rupture other than the historical mode of slip at the site. I'll just plug the idea of using structure from motion for really detailed geodetic studies of change, tectonic geomorphic change along faults. So this is from our model of structure from motion at this site in 2014 was used with a DJI Phantom and GoPro, and now we're using quite a bit of a better camera, still on a DJI Phantom, double the resolution, much less distortion in the lens and that we're using, the lens and sensor. And so here we're showing a differencing from 2014 to 2007, as well as the two models profiles over the top of one another. And we don't really see any evidence of overall warping or bowing of the model. And there's some general consistencies with what we'd expect in terms of the differencing. So that is, the sag pond appears to be dropping down, the scarps appear to be rising. So this is a good amount of potential for other important studies. Okay, so that I'll just say that our conclusions are that there's no evidence for large surface ruptures preserved at the DLV site. Of course, there's the potential that we could be hiding something in the wide, highly deformed zones of these creeping fabrics, because you can imagine there's 100 plus to 200 meters of displacement through the zone of the oldest stratigraphy. And so overprinting could present a problem for interpretation if there were filled fissures and things like that. But on areas where it's quite simple, we just have primarily things like colluvium coming across the site. We don't see any evidence for colluvial wedges over the last couple hundred years. And then finally, surface creep in the absence of surface processes may confound interpretations of earthquakes in high and dry slip rate environments where there's creep. And then lastly, short aperture and short-term creep measurements are consistent with wide aperture, both geologic and geodetic slip rates as seen by this site.